Hi everyone, my name is AnthonyHennig, and I'm an undergraduate researcher in mechanical engineering here at RIT. Today, I'd like to talk to you about biomimetics and air muscles. So, what is biomimetics? What does it mean? Well, biomimetics comes from the fundamental concept of engineering, the iterative design process. The idea that you have a problem. Then you come up with a variety of solutions, you try them out, and out of those solutions, some of them succeed and some of them fail. Biomimicry says, hey, nature's been doing this iterative design process for the past billions and millions of years. And from that, we can do some really cool things. We can use nature as a jumping off point for our designs. We can use nature as a way to make our designs that we currently have, that we've created, even better. And we can also use nature as a way to measure our designs in their terms of efficiency and versatility. What are some examples of this? There's two really cool ones. One of them involves the dormal denticles of the shark, or the shark skin. Biologists, looking at the shark scales underneath an electron microscope, found that they had no bacteria on them whatsoever. Material scientists took this design pattern and copied them over onto a material that they now call sharklet. Sharklet is incredibly unique in the case that you don't need disinfectants or microbial agents to clean them. They stay clean by themselves. Another really interesting example happened when biologists looked at the feet or the paw of a gecko, a creature that can scale essentially flat vertical walls with great ease. Material scientists were able to take that design and copy it over into something that they're calling gecko tape, which is incredibly strong and is probably one of the strongest adhesives ever created. Where do air muscles fit into all of this? Well, air muscles came out of the attempt by J.R. McKibben in 1956 to emulate human muscle. This is what he developed. What you see here is a rubber bladder surrounded by a woven sheath. It's closed on one end and open on the other to let air come through and pressurize the vessel. The idea is that when you pressurize this air muscle, the rubber bladder, just like a balloon, expands. And surrounding it, this nylon sheath ultimately limits its contraction. Because this nylon sheath is now expanding, less material is contributed to its overall length, and it contracts, causing a pull force. Now, why would anyone want to use this? Well, first off, J.R. McKibben got it right. Pneumatic air muscles act, look, and function just like real human muscle does. Furthermore, these systems are incredibly strong and lightweight. This one's about 20 grams and can lift about a kilogram of weight. Furthermore, they're also incredibly low cost, this one being made for $5–10 with off-the-shelf components. They also have smooth action-reaction. Have you ever played with an electric motor and noticed how it kicked or suddenly jerked as it started to move? Air muscles don't do this. Furthermore, because the entire air muscle is enclosed, you can put this in a variety of environments that other pneumatic actuators simply wouldn't work in. Pneumatic air muscles, just like this one, can function underwater in dirty or dusty environments and have no problems whatsoever. So, where are we seeing them starting to be used? Well, one of the really exciting new fields is using them in prosthesis to emulate human muscle systems like the shoulder, the arm, the leg. We also see them in biomimicry applications, where one company was able to take a healing limb and modify it to act just like a manta ray, powered with nothing but air muscles. We've also seen them being used in robots that try to mimic bipedal or quadrupedal movement. Here at RIT, we've worked with them in the context of the human hand and arm muscular system. We've worked with them in underwater capacities, making a biomimetic crab that functions at the bottom of a pool, and also working with self-autonomous systems and self-contained systems with a large biomimetic ant. You can turn it on, it will simply go on, doing whatever it wants to do. So I bet right now you're really interested in how to actually make them. To do this, you're going to need a few things. You're going to need an off-the-shelf air fitting, a regular eye hook that you pick up at a hardware store, some rubber surgical tubing, a nylon sheath, and usually some zip ties to help close everything off. To assemble the air muscle with the eye hook and the rubber tubing, put them inside of each one of them. Then take your nylon sheath and fit it over the rubber tubing. Then take your pneumatic air fitting and put it into one end of the nylon sheath. This rate, the entire system is enclosed. Now, take your zip ties and put them around both ends of the pneumatic air muzzle so that underneath them you have sheathing, rubber, and then metal either from the hook or from the air fitting. Make sure to get them very tight. We don't want any air leaking through. Now, take your pneumatic air muzzle and hook it up to an air feed. And then, pull on that feed. Congratulations, you just made your own pneumatic air muzzle.